SFT teaches the approved answer, but DPO learns which answer people prefer. TRL lets you train both and measure when preference pairs change behavior. You'll see how to connect the pieces into a workflow that trains two answer improvement paths and picks the stronger one with held-out preferences. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Start with the practical problem. You have prompts and human judgments that say which completion is better. You want a model that not only copies good answers, but reliably prefers them over bad ones on new prompts. Many teams run supervised fine-tuning because it's straightforward, but it drops the direct signal that one completion beats another. That difference matters when you care about ranking, safety, or nudging the model away from harmful outputs. The core idea is simple. SFT copies the chosen completions and ignores the rejects. DPO trains on pairwise preferences, so the model learns to give higher probability to the chosen answer than the rejected one. Think of it as two paths: imitate versus prefer. We'll build a tiny workflow that uses the same raw rows for both methods, holds one pair out for evaluation, and then checks which training path better lifts the chosen answer above the rejected one. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now, let us prepare the smallest preference dataset we need and hold a row for evaluation. This snippet creates the smallest preference dataset needed for a DPO versus SFT comparison. Teams often have rows like this already: one prompt, one approved answer, and one rejected answer. Dataset.fromList turns the readable raw tuples into the explicit prompt, chosen, and rejected format that TRL expects for preference training. The deterministic split keeps one row held out, so every later training choice has the same evaluation target. The output confirms the dataset size and the held-out count, which matters before comparing any training result. With that held-out pair in place, we now shape the baseline data to be a pure supervised replication of the chosen completions. To run SFT fairly, create an SFT training set by turning chosen into completion and dropping rejected rows. This code keeps the approved answer path while discarding the ranking signal. That is the baseline many teams run by default. Turn chosen into completion, remove rejected, and train only on demonstrations. The important part is that SFT train comes from the same pref train rows, so SFT is not getting extra examples or easier prompts. SFT test mirrors that shape for completeness, while pref test stays available for pairwise evaluation. The output shows the SFT row count and a real approved completion, making the baseline data visible before training. Before we train, it helps to know whether the base model already prefers chosen over rejected. Score the two completions on the held-out prompt using average log probability over answer tokens. This example measures whether the untrained baseline already prefers the approved answer. The log_p function scores only the answer tokens after the prompt, which keeps the comparison focused on the competing completions rather than prompt wording. AutoTokenizer builds the input. AutoModelForCausalLM produces logits, and the code compares average log probability for chosen versus rejected. This is a compact teaching metric, but it represents the same core idea behind a held-out pairwise preference check. The output shows the base model's log probability gap, giving you a pre-training reference point. Next, we train the supervised baseline with the exact same prompt completion rows, so the comparison stays fair. Use TRL's SFT trainer with a tiny reproducible config, so results are consistent on toy data. This snippet trains the supervised baseline using TRL instead of treating the toy data as a custom loop. SFT config sets a tiny reproducible run with seed, max steps, and report to, while SFTTrainer consumes the matched SFT train prompt completion dataset. The key limitation is intentional. SFT sees only approved answers, so it can imitate good completions, but does not directly learn from the rejected alternatives. Increasing max steps gives the trainer more updates, but on tiny data, it can also make the comparison noisier. The output shows the held-out chosen versus rejected gap after SFT, so the baseline has a measurable result. Now, train the preference-aware path, so the model learns from pairwise wins and losses. Run DPOTrainer on the same pref train rows, and evaluate both models on the held-out pair. This code runs the preference-aware alternative on the same prompts and approved answers. DPOTrainer receives pref train with prompt, chosen, and rejected, so the ranking label is now part of the training signal instead of being thrown away. The win rate helper evaluates both trained models on the same held-out pair and counts whether chosen scores higher than rejected. With real experiments, this is where tracking multiple seeds and larger held-out sets becomes important before declaring DPO useful. The output puts SFT and DPO side by side, which is the comparison needed to justify preference training. If you take this toy mapping to production, the pattern is the same. Keep the prompt rows identical between SFT and DPO. Hold several pairs out, and measure pairwise wins instead of just loss. That gives you a direct signal about which method actually shifts ranking behavior. What we did: we prepared a minimal preference dataset, trained SFT to imitate chosen answers, then trained DPO to prefer chosen over rejected, and compared them on held-out pairs. When to try this? When you have small but reliable human pairwise labels, and you care about ranking the best answer above the rest. One caveat: toy runs on tiny data are noisy, so do not declare victory without more held-out pairs and multiple seeds. A practical next step is to collect a larger held-out preference set and rerun the comparison across multiple random seeds to get a stable win rate estimate for DPO versus SFT. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.